Similarly, you can go for comparing lambda squared on both sides. We will get the second order perturbation equation. Okay, and goes on. So equation 4.12, 4.13 and 4.14 are termed as unperturbed first order and second order perturbation equations respectively. Okay, it is convenient to normalize the following transition amplitude. We are going to look into now using equation 4.9. Now this is your equation 4.9. Okay, psi n expansion in terms of lambda we know already. Now you just pre-multiplying on both sides by bra psi n. So just consider this as ket psi n. You just multiply with bra psi n on both sides. So you will have bra psi n 0 with ket psi n, which is equal to this one, bra psi n 0 with ket psi n 0. The lambda you pull it out, it's a number parameter. So lambda, then we have psi n 0, bra psi n 0 with ket psi n 1 goes on. Okay. Now you just compare again with lambda to the power 0, lambda to the power 1, lambda to the power. You just compare. We will have the first part alone will be equal, correct? This will be lambda to the power 0 and this will be lambda to the power 0. What are the other terms? Here there is no lambda, here there is no lambda square at all. So this will be equal to 0. So this part alone will have 1. So this part alone will have 1. All the other parts will have 0. Lambda is a number, as I said, cannot be equal to 0. So these two can be equal to 0. It implies that these two wave functions are orthogonal to each other. They are normalized. Is it okay? They are orthogonal and they are normalized. See, they are normalized one. So equation 4.18 implies that they are orthonormal eigenfunctions. The corrections to the wave functions are perpendicular always. Okay? Is it okay? Now we are going to evaluate the first order correction to the energy En1. The first order perturbation is given by equation 4.13. We have already seen this one. Okay, equation 4.13 we have taken in terms of lambda to the power 1 equation, comparing the coefficient lambda to the power 1. We have taken this equation. So this equation is called first order perturbation equation. Okay, we just take this. So psi 1n can be expanded in terms of expansion theories. We know already, we discussed earlier. So psi 1n can be expanded in terms of expansion series like Cm, psi m. Cm is expansion coefficient. Psi m is another index. So we know already this. Okay, where psi m is given by psi 1, psi 2, psi 3 and goes on. Now substitute equation 4.20 in 4.19. So we have 4.19 is here. We just substitute here. So we have h naught. Instead of psi n 1, you substitute Cm psi m. So Cm psi m 0. Is it okay? So this equation is 4.19. This equation is 4.20. Okay. We are going to substitute this expression into this expression. So we have h naught psi n 1. Instead of psi n 1, you substitute this. So we will have Cm h naught psi m 0. Is it okay? Plus h1 psi m 0 as it is. Which is equal to En is here. Psi n 1. Psi n 1 is nothing but Cm psi m. So Cm psi m 0. And that expression let it be like this. See, for this alone we are going to substitute. Psi n 1 is expanded. All the other terms are let it be like this. Now we know already for unperturbed Hamiltonian energy eigenvalue, we know already this. So we know already this. Correct? H naught acts on psi m 0, which is equal to Em with psi m, we know already this one. So now H naught psi m can be written as in terms of Em psi m. So substitute for this expression alone. So we will have Cm, Em psi m 0, correct? And you bring this term to this side, this term, okay, to left hand side. So we will have left hand side. And rest of the term let it be like this. And right hand side we have one equation, Cn1 psi n 0. Is it okay? Now pull the common terms out in first two terms. So we have Cm. Okay, here we have Cm. Mistake is there, Cm. Okay, so Cm Em minus En psi n 0. Okay. The remaining term, H1 psi n 0, En psi n 0. Is it okay? Now you just multiply, pre-multiply by complex conjugate of psi n. Just pre-multiply. So we have Cm, Em minus En. So we are going to multiply, pre-multiply with psi n 0, complex conjugate of this psi n 0. So we will have psi m data. Plus we are going to multiply with this. So we have psi n complex conjugate. Then H1 is there. We have psi n data. So which is equal to psi n complex conjugate of psi n En1 psi n data. Is it okay? Any doubt? So what we have done? Just take the common term out and multiply with complex conjugate of psi n. That's all. So we have obtained equation 4.25. Okay. Now we know already the canonical delta function is given by this. We know already this condition. So when n equals m, the answer is 1. When n is not equal to m, the answer is 0. We know already this. So according to this condition, the first term becomes your psi n psi m. Okay, first term is 0. Okay, because n and m, they are different. N is not equal to m. And this one, let it be like this. You have psi n, see psi n h sandwiched between psi n and psi n star. Okay, it's a complex term, which is equal to the last term, your En is a number. You can pull it out. So En psi n star psi n d tau, which is equal to 1. So En1. Is it okay? Come on. The first term is they are different, so this will become 0. Second term as it is, the H1 sandwiched between your ordinary complex wave function and its complex conjugate. Let it be like this. And the term on the right hand side will be, you just pull En out. So you will have psi n star psi n d tau, which is equal to 1. So you will have the answer exactly like this. So your En1 is equivalent to this. Correct? En1. What is En1? It's a first order corrected energy. Correct? En1. En0 is unperturbed term. En1 is first order correction energy. En2 is second order correction energy. It goes on. So we have calculated now En1. So En1 equals, in terms of wave function, in terms of Keck-Bra notation. So your H1 sandwiched between your Keck psi n and Bra psi n. What is this one? This is the expectation value. The expectation value of the H1 perturbed system. So this is perturbed system. Your H will be H0 plus lambda H1. Correct? Lambda H1. Can you remember? Your H will be H0 plus lambda H1. Lambda H1. H1 stands for perturbed system due to some external perturbation. It's a matrix element. So this is the corrected energy. Okay. So equation 4.27 gives the first order perturbation of the energy eigenvalue. So this equation can be written as exactly like this. Is it okay? So we have come to the end. So it indicates that the first order energy correction for the non-degenerate system is nothing but the expectation value of the first order Hamiltonian. And substituting in 4.8. So this is equation 4.8. We need to have complete energy. So this is En1 alone. We need to have En. So we need to have En. That is our eigenvalue equation. Can you remember? H psi n equals En psi n. So En stands for your complete total energy. So En equals En0 plus lambda En1, which we have calculated now. You substitute for En1. So En equals En0, unperturbed energy for the unperturbed Hamiltonian, plus lambda, this term. Plus lambda is there. Psi n1 is nothing but this term. Is it okay? So we have calculated now energy eigenvalue for the perturbed Hamiltonian. If there is no perturbation, lambda becomes 0. Lambda will not be there. So En becomes En0, which is unperturbed energy. So it's correct. Is it okay? So now we'll go for the wave function. So we have computed for energy eigenvalue. Now we'll go for the wave function. As usual, we'll have to obtain two things. One is energy eigenvalue and another one is wave function. So we have obtained energy eigenvalue. We are going to obtain wave function. That's all. So now just take equation 4.21. Just take 4.21. Equation 2. Just pre-multiply with psi m star, psi m 0 star. Pre-multiply. So we have Cm. Okay, pre-multiply. So psi m 0, okay, star h0 psi m 0 plus your lambda is there, correct? Sorry, h1 is there. So you have psi m 0 h1 psi m 0, which is equal to Cm em 0 psi m 0 star psi m 0 plus En, that is there, your psi m 0 star, your psi m. We know already eigenvalue equation for the unperturbed Hamiltonian equation is given by we know already. We are going to substitute here. So this equation h0 sin psi m 0 can be written as em 0 psi m 0. So em 0 psi m 0. Right, other terms and all, let it be like this. Just take the common terms out. You pull this one, bring this term here, and just take the common terms out. Correct? And this term let it be like this. And this term will be the last term, right hand side and last term will be exactly like this. Is it okay? Now we are going to integrate on. So we have integrated into the space on either side. Is it okay? I repeat. So these two terms can be written in terms of eigenvalue equation exactly like this, and you just bring this term this side, left hand side, common terms out, that will give you this term. Okay, remaining term and all, let it be like this. What if this term right hand side, here it is psi m psi n, so it must be 0. We'll have to use again Kronecker delta function. Okay, when n equals m, answer is 1, not equal to m, which is equal to 0. So this term will not appear. So this will become 0. We have this term plus second term in the left hand side. Okay, these two terms. Okay, any doubt? Now your Cm will be this term divided by this term. Okay, this term divided by this term with a minus sign. So now we know Cm. You substitute here in the expansion coefficient. Cm is nothing but expansion coefficient. So substitute in the expansion theorem. So your psi n1 is given by Cm multiplied by psi m0. So Cm is given by this expression multiplied by psi m0. So this is your wave function for the first order. Okay. Now complete wave function will be psi n equals psi n0 plus lambda psi n1 plus lambda squared psi n2. So just to substitute this expression psi n1 here. So you will have psi n equals psi n0. Correct, here minus is there. So minus lambda, instead of psi n1 you just substitute this expression with psi m0. Okay. So this is the complete wave function we have calculated for the first order perturbation energy. Okay, wave function. This is the expression for the wave function with the inclusion of first order perturbation. Is it okay? Now what we have done so far. So the perturbation method is valid when the Hamiltonian can be split into two parts. One is unperturbed, another one is perturbed one. Unperturbed is the exact solution which we have already done using Schrodinger wave equation. We have obtained wave function and energy eigenvalue, we know already. Okay. Then second part will be we are going to solve using expansion power series method, and this should be very, very small. The total Hamiltonian is partitioned into perturbation terms like lambda h1, lambda squared h2, lambda cube, h3 goes on. We are going to find a suitable zeroth order Hamiltonian whose eigenfunction eigenvalues are known already, exact method. We expand the energy and wave function into smaller and smaller parts. Equate the terms lambda to the power 0, equate on both sides, lambda to the power 1, lambda squared on both sides. You can also obtain second order. We have done only for the first order, correct? You can also obtain second order, third order, and those things will be very, very small. Lambda itself very small. Lambda squared, it will be small. For example, just take lambda equal to 0.2. Lambda supposed to be 0.2. Then lambda squared will be point. Come on. Lambda will be 0.2. Your lambda squared will be very small. It will be again very small. It will be 0.04. It will be very small. Okay. So equate the terms according to the powers. Powers of lambda 1, lambda 2, lambda 3 goes on. The power of perturbation. Okay, the order of perturbation. Use completeness. We have done normalization, completeness, and orthogonality. We have used Kronecker delta function, correct? Of zeroth order eigenfunction in order to obtain the corrected energies and the wave functions. Now we will go for one problem. Any doubt? So problem 1. So we are going to solve only one problem using perturbation theory, time independent perturbation theory for stationary states. Consider an infinite square well expressed by this condition. Your v of x equal to 0 when x lies between 0 and L, and v of x equal to infinity otherwise. Using the first order perturbation theory, calculate the energy of the first two states. First two states means n1 equal to 1, n1, n2, n1 and n2. N equal to 1, n equal to 2, or n1 and n2. Calculate the energy of the first two states of the potential well if the portion is defined by exactly like this. The portion is, this is called a sliced infinite square well. See, sliced. It is not a uniform square well, correct? It is not uniform infinite square well. Just look at, so this is a sliced infinite square well. So perturbation has taken place. So we know that the energy eigenvalue and the eigenfunction of the unperturbed Hamiltonian is given by this expression. We know already. En is given by this expression. We know already, we studied earlier for the infinite quantum well. For the exact solution, we know already this. So in unit 2, we already studied. Now the perturbation is given by this expression V naught x by L. Okay, V naught x by L. Here V naught x by A is given, but V naught x by L. So this is V naught x by L. So our H prime equal to V naught x by L. Now the first order correction which we learned just now, equation 4.28. Just now we looked into, this is given by the energy for the first order correction is given by the expectation value of the Hamiltonian, first perturbed Hamiltonian. Can you remember? So this is the first one. So H1 sandwiched between your ket psi n 0, bra psi n 0. H1 is given by V naught x by L, correct? So instead of H1 you just substitute V naught x by L. Okay, your psi n, just now see, this is expression for psi n. Psi n 0 is given by root of 2 by L sin n pi x by L. So psi n 0, we'll have to use that one. Take the complex conjugate for psi n 0. So this is a ket psi 1. That will be your ket psi 1. Taking the complex conjugate will give you bra psi n 1. So you will have to multiply 2 times, correct? Multiply 2 times. So root 2 by L multiplied by root 2 by L will give you 2 by L. Your V naught by L is constant, I have pulled out. Remaining time will be x sin squared n pi x squared. So you have x here. This should be multiplied squaring. So that will give you sin squared n pi x by L. We will go for first n equal to 1. For the first state, n equal to 1. So you will get 2 V naught by L squared x sin squared n equals 1. So pi x by L. We know already sin squared x equals 1 minus cos 2x by 2. So we have x by 2. You just pull x by 2. Remaining term will be 1 minus cos 2 theta. So 2x. So 2 pi x by L. Separately, you can do separately. This side and that side with a minus sign here. Separately you can integrate. So that will be the first integration will be your x dx. That will give you x squared by 2. Substitute, that will give you L squared by 2. And the next term will be, just you go for the assignment using u dv equals uv minus v du method. Just keep this as u, this as dv. You will get exactly 0. You will get the answer as 0. So that will be your assignment 1. Okay. So just add these two, that will give you V naught L squared by L squared 2, L squared will cancel, you will have En1 equals V naught by 2. Okay. Therefore the corrected energy. What is the corrected energy? En equals, usually we will calculate E0 plus lambda E1. Correct? This is what we have done so far. So this will be your exact energy. This will be from perturbed first. Okay, first order correction for the perturbed one. So we have already done V naught by 2. Okay, V naught by 2. So now this will be your n equal to 1. So that will be given as pi squared h bar squared divided by 2m L squared plus V naught by 2. For n equal to 2, you just follow the same procedure for n equal to 2. So that will become, where wave function will become, for n equal to 2, you will 2 pi x by L. So 2 pi x by L, same procedure. Okay, you will get the same procedure, you will get the same answer. Okay, for n equal to 2, you have to go with 2 squared. So you will get 4 pi squared h bar squared divided by 2m squared plus V naught by 2. You will get same answer. See here, you will get same answer. Here also you have x. You will get the same answer, V naught by 2. So V naught by 2. This alone will vary. Okay, this alone, because n equals 1 here, here n equals 2 here. This alone will vary. Last time also we got for n equal to 1 V naught by 2. This time also we got V naught by 2. So V naught in terms of electron volt. So this also in terms of electron volt. Okay. So only thing is, see, you have an infinite quantum well. For n equals 1, you have certain energy level, correct? So those energy levels are discrete energy levels in a bound state, because electron is inside the well. So we will get only discrete energy levels. So those cases are bound states. Now, when you are going to disturb the system, this energy level will change with addition of V naught by 2. Is it okay? This energy level will change. Either it can go up or it can come down. So there will be change. So that's why we have added with the exact solution. So this is the exact solution for n equal to 2. This is the exact solution for n equal to 1. We have added the perturbed energy. So this is your perturbed energy. You will get the total energy. So that's the idea. Okay. So the corrected energy levels are lifted by the amount V naught by 2. Okay. You need not always think this will be lifted. It can also come down. So there will be change in energy. For first order, answer is plus. Correct. For first order, answer is plus. It can be also minus for the second order, third order. We can't say. There will be change in energy level. So we have to add or subtract with the exact energy to get the total Hamiltonian for the perturbed system. So that's the end. Okay. So thank you, students. We will see in the next class.